So I have this discrete random variable x with this probability distribution p of x. So the probability that x is 1 is 2/10, probably that x is 2 is 2/10, probably that x is 3 is 1/10, probably that x is 4 is 1/10, probably that x is 5 is 1/10. And we're asked to find a few things. We're asked to find the expected value, the variance, and the standard deviation. So to find the expected value, so I'm going to use, I don't know. Oh, okay, no problem. If you got to leave early, I totally understand. So whenever we're trying to find the expected value of something, most people, I don't know if your teachers use this notation, but we often use the notation, right, the sum. Here we have the sum as x goes from 1 to 5 of x times the probability of x. It's just a weighted probability or a weighted mean, right? You're just taking every value of x and multiplying it by its corresponding probability. So it's the value of 1 times probability of 1, the value of 2 times the probability of 2, plus the value of 3 times the probability of 3, plus the value of 4 times the probability of 4, plus the value of 5 times the probability of 5. We add them all up, so let's see, it's going to be 2/10. It's going to be 2/10 plus 4/10 plus 3/10 plus 4/10 plus 20/10. And since they all have the same denominator, I can just write them over one fraction. And then that's going to be, let's see, 20 plus 4 plus 3 plus 4 plus 2 is 33, I think. Let's see, yeah, 33. So 33/10, which is 3.3. That's not terrible. 2, 4, 3, 4, 20. Yeah. Okay. So then we want to find the variance. So the variance is you take all of your values again, you see how much they differ from the mean, you square that, and you multiply it by its probability. So the formula for that is the sum over all the x values, here x is going from 1 to 5, of x minus the mean, which we can write as mu, or we can write as the expected, right? This is just another name for the expected value, squared times the probability of x. And I will mention these formulas are important because they're going to pop back up in a continuous form with an interval. So that's kind of one of the reasons I'm talking about them, because we're definitely going to see these again when we talk about the continuous random variables and how to calculate their mean and variance and standard deviation. So this is going to be, so we're going to do, and this is going to probably require some calculator work. So we're going to have 1 minus 3.3 squared times 2/10 plus 2 minus 3.3 squared times 2/10 plus 3 minus 3.3 squared times 1/10 plus 4 minus 3.3 squared times 1/10 plus 5 minus 3.3 squared times 4/10. And to be really frank, I don't think it's that vital that we actually I think the calculator work here is something you all could do on your own, right? I don't think me sitting down on a calculator for a minute is going to be super illuminating, but that's what we're going to get. I will point out that there are lots of ways to calculate these things without having to actually write it all out. Now your teacher might want you to write it all out, but they might just say you can plug it into a calculator. I'm wondering if there's a way to do it on this calculator. It doesn't actually look like it, but oh, there's a stop button. Let's see here. Yeah, there's totally a stop button. So if you look on the calculator, there's often a stop button with like one variable stats. I think I actually want to go over to the distribution here. Yeah, I don't know. Probably not. It's probably, I don't know. It might not be so great here. Right. This one might be hard to do because you're given kind of just all the probabilities and not a number of data points. But we could totally calculate that. And then the standard deviation is just the square root of whatever that was. So there's another example of a discrete random variable with a probability distribution. Questions about this one before we move on to some continuous ones? I will point out one more thing. We know it is a discrete, a discrete random variable with a probability distribution because all the probabilities are non-negative, less than 1, and all the probabilities add up to 1. Right? That's always a requirement. So if someone gave you this and said, is this a probability distribution of the random variable x? We would say yes, because 1, all the probabilities are positive, or really non-negative, and less than 1, and 2, they all add up to 1. If someone did something silly, like said, this is my probability distribution, where it's a negative 4 tenths, you say that's not a probability distribution, you can't have a negative probability. Or if someone said my probability was this and this value here was 6 tenths, you would say, well, that's not a probability distribution either, because they don't all add up to 1. So we have to have those two things being true, that the probabilities are all between 0 and 1, and they all add up to 1, which is going to be true in the continuous sense as well. So let's look at some continuous examples, and we got lots of examples here. So for continuous examples, the idea is the same. The probabilities should all add up to 1. But when we know when we're talking about continuous things and we're adding things up, we're usually integrating. So let's look at this example. This pen is starting to wane here. So the weight of a potato at harvest in pounds is modeled by the probability density function. People often abbreviate as a PDF, not to be confused with a document. F of x equal to 3/14 times the square root of x on the interval where x is between 1 and 4. So first of all, let's actually verify that it is a probability density function. I said it was, let's show it is. So there are two things that have to be true for something to be a probability density function. The first is that the function needs to be non-negative on the interval. Check, right? It is definitely true that this function equal to 3/14 times the square root of x. This is always greater than or equal to 0. Actually, no matter what x is, but certainly on the interval from 1 to 4. Okay, that's an easy thing to disqualify something, right? If something is ever negative, you're like, oh, that can't be a PDF. The other thing we have to check, and this is the more important thing, is that the area under the curve has to equal 1. Right, just like all the probabilities have to add up to 100% or 1, here all the probabilities have to add up or have an area of 1. So let's go ahead and check that. So we're going to do the integral from 1 to 4 of our probability density function of 3/14 times x to the 1/2. So we're going to integrate. We're going to get 3/14 times the integral of x to the 1/2 is x to the 3/2 times 2/3. Sorry, door just slammed. I think it's because we have windows open. I might need to go check on that in just a second. Fine, why don't you guys finish this integral while I go make sure there's a door that doesn't need to be open. I'll be right back. It should equal 1. Yes, my wife definitely wanted that door open. So good thing I got one left. All right, so let's see. 3/14 times 2/3, we can cancel a 3 and a 2, cancel the 2 here. So we're left with a 1/7 times x to the 3 halves. And then we're going to get 1/7 times 4 to the 3 halves minus 1 to the 3 halves. 4 to the 3 halves is 8, right? It's the square root of 4 cubed, which is 2 cubed, which is 8. So you get 1/7. It's really amazing how you can say something or write something totally different. 1/7 times 8 minus 1, which is exactly 1. Check. So great. It is a PDF. And again, to be a PDF, the two things that have to be true is that f of x has to be greater than or equal to 0 on the interval that you're looking at. And the integral on that interval of your function must equal 1. Those are the two requirements for a continuous function to be for functions modeling continuous probability, for it to actually be a probability density function. Great. So what that looks like okay. The scale here is kind of it's like a 1/2. Just like a 1. My y scale is going to be a little bigger, so it's a little bit nicer. Let's see, this is 3/14. It's going to be 6/14. So here's kind of what my function looks like on that interval. What we just showed is that this area under the curve, right, that has an area of 1. So now we can ask questions about, I can update my Zoom, I'll do that later. We can ask questions about what the probability of a potato having a certain range of weights is. So you say, like, what's the probability that the potato weighs between 1 pound and 9/4 of a pound? Normally I would probably ask 1 and 2 pounds, but the interval is easier if we use 9/4. So, yeah. So what's the probability that you have a potato that weighs between 1 pound and 2.25 pounds? So that's about like right there. And so the probability of that is just going to be how much of the area we have. So whatever that area is right there, that area is equal to the probability that our potato weight, let's call it x. That's the probability x. Yeah, sure. That's the probability that x is between 1 and 9/4. Well, we know how to find the area under a curve between 2 points. We use an integral. So that's going to be the integral from 1 to 9/4 of the same probability density function. 3/14 times x to the 1/2. We've already integrated this, so we know how to do it again, right? The integral of 3/14 x to the 1/2 is 1/7 x to the 3 halves. Right? We did that work on the other side. The integral ended up being this, which was 1/7, right? All that there is just 1/7 times x to the 3 halves. From now 1 to 9/4. So we plug in 9/4. Let's factor out 1/7. So 1/7 times 9/4 to the 3 halves minus 1 to any power is just 1. 9/4 to the 3 halves. Okay, so it's the square root of 9/4, which is right? This is going to be the square root of 9/4, which is 3/2 cubed. And 3/2 cubed is going to be 3 cubed over 2 cubed. So you get 27 over 8. It's going to be 1/7 times 27 over 8 minus 1, which is minus 8 over 8. So you get 27 minus 8, which is 19 over 7 times 8, which is 56. So you get 19 over 56, which is a little bit bigger than a third. Okay, that seems reasonable. That the way I've drawn it looks like that could be about 1/3 the area. Doesn't mean your picture has to look right, but that's the idea. We could also ask, yeah, let's go over here. What's the probability that the potato weighs more than 9/4 of a pound? Well, we could do the work, or we could do, and so I should say more than 9/4 of a pound, but still less than 4, right? Because we limited ourselves to an interval where the potatoes were weighing between 1 pound and 4 pounds. So we could do the integral from 9/4 to 4 of the same 3/14 times x to the 1/2 dx. But we're not going to do that because we already know stuff. We already know that all this area is 1. We just figured out that this red area is 1956. So I want to find this remaining part, which is what I'm asking, right? If I'm trying to find the probability of being between 9/4 and 4 pounds, I can say, oh, well, this area is just 1 minus that area. So that's going to be equal to 1 minus the integral from 1 to 9/4 of 3/14 next to 1/2, which we already calculated. Another way of saying that is that the probability that x is between 9/4 and 4 is equal to 1 minus the complement. The complement's all the other stuff. So instead of being between 9/4 and 4, it's being between 1 and 9/4. That's the complement. Right? It's all the leftovers after you look at what that is. Well, we calculated that, so that's going to be 1 minus 1956, and 56 minus 19 over 56 is going to be 37 over 56. So basically, right, the two probabilities should totally add up to 1. So we can say, well, if I know one of them, I can subtract it from 1 to find the other one. Let's talk about the expected value. I guess I want this picture. So for discrete probabilities, which we just saw earlier, the expected value is the sum of all the x's times the probability of x. Well, it's the same idea here. Except now, right, you're taking all the weights and add and multiplying by the probabilities. But the problem is there's an infinite number of possible weights. So we're going to find the expected value here as the integral, where we're adding up all of the possible weights, x, times their probabilities, p of x, except it's a probability density function, so we call it f of x instead of p of x. It seems kind of silly, right? I feel like we should just call it p of x, but that's not what we called it. It's called f of x. From a to b. This is the general formula. And specifically for this function, our expected value is going to be the integral from 1 to 4 of x times our probability density function, which is again 3/14 times x to the 1/2. Okay, so now it's going to be a different integral. So x times x to the 1/2 is x to the 3/2. So we have the integral from 1 to 4 of 3/14 times x to the 3/2 dx. We're going to integrate that. Oops. Which means you don't need the integral, right? If you're integrating it, you don't need the integral symbol anymore. So if we anti-differentiate this, we get 3/14 times the integral of x to the 3/2 is x to the 5/2 divided by 5/2, or x to the 5/2 times 2/5 from 1 to 4. 2 and a 4 canceling you a 7. So you get 3 over 7 times 5. So that's going to be 3 over 35 times 4 to the 5/2 minus 1 to the 5/2. 4 to the 5/2 is 2 to the 5th, which is 32. 32 minus 1. So you get 3/35 times 31, which is 93/35. So the expected value is pretty close to 3. It's a little under 3, right? Because 105/35 would be 3. Okay, not too bad. So let's talk about the variance. The variance is kind of a pain in the butt. Well, it can be, but it doesn't have to be. So let's talk about, there's 2 different formulas for the variance. One of them is almost always the better formula. So, and again, let's kind of talk about discrete versus continuous. So discrete, right? Our expected value formula is the sum of all the values times their probabilities. And the continuous, it's the same idea, really. The expected value is the sum of all the values times their probabilities. We're just calling the probabilities f of x instead of p of x. For the variance, in the discrete version, again, we're adding up all of the differences in the x values and the mean squared times their probability. Which here it's going to be the same idea. The variance is going to be, we're going to add up all the x's minus the means squared times their probabilities. Now the issue with this is that it's gross, right? So this is like for our previous question, right? Our mean is 93/35. And right, we plug this in here, we're then, so let me just, I really don't even want to do it. I will write out the formula, but then I'll write out how it would look, and then I'm going to show you the easier way, because doing it here is really awful. So here's what we would have to calculate. We would have to find the variance. It'd be the integral from 1 to 4. I should probably have some A's and B's here. But for this particular example, the integral from 1 to 4 of x minus the mean squared times your probability density function, which was f of x, which was 3/14 times x to the 1/2. Someone was really yelling outside. It's kind of concerning. Okay, so hopefully you guys can see this is a giant pain to multiply. So if you do this, it's going to be the integral from 1 to 4. Multiplying this out, you're going to get x squared minus 2x times 93/35 plus 93/35 squared, all times 3/14 x to the 1/2. And then you would have to distribute this to each of these terms. And then you'd have to integrate each of them. And then finally, you would plug in this. But you can see it's kind of a lot of pieces. which if we had to do it would be fine, but there's a better way. So let me show you the better way. This is kind of slick. So watch for a minute, because your teacher hopefully showed you this, but if they didn't, I think it's worth noting. So there's an alternate formula. Here's how you get there. I'm going to take this and I'm going to multiply it out. So I get the integral of x squared minus 2x times mu plus mu squared, all times f of x. And again, this is the variance. Okay. Well, now I'm going to distribute. So I'm going to get the integral from a to b of x squared times f of x minus 2 times x times mu times f of x plus mu squared times f of x. I'm going to break this up into 3 integrals, and I'm going to pull any constants out. And specifically, 2 is a constant, and mu, the actual expected value, the mean that we've calculated. In our particular example, it's 93/35 or whatever. We're going to factor that out as well because it's a constant. So let me show you what we get. We get the first integral is the integral from a to b of x squared times f of x dx. The next piece we're going to get, I'm going to factor out the minus 2 and the mu. So I'm going to get a minus 2 mu times the integral of x times f of x. And then we're going to get plus, I'm going to factor out a mu squared, the integral of f of x dx. Okay, so now I have a couple questions for you guys. Can anybody tell me what the integral from a to b of f of x has to equal, since f of x is a probability density function? Exactly. Thank you, Joanna. Sorry, I didn't want to. There's a direct message. I apologize, but you're correct. It is definitely 1, right? Because, right, the integral of the function over the interval has to equal 1. So that's 1. Okay, slightly harder question, but the answer is on the board. Can anybody tell me what the integral from a to b of x times f of x dx is equal to? It is on the board. Exactly. It is the expected value, right? The integral from a to b of x times f of x is exactly the definition of the expected value of x, or mu, if you want to use the word mu. So this is equal to mu. So look what we've got. We've got the integral from a to b of x squared times f of x minus 2 times mu, or 2 mu squared, plus mu squared times 1. So the alternate version of the formula for the variance, which is the preferred version, is that the variance is equal to the integral from a to b of x squared times your f of x. That will have to be calculated. Minus 2 times the mean squared plus the mean squared is minus 1 of the mean squares. And that is outside of the interval. So that is the version of the variance formula that I would encourage everyone to use every single time. So let's look back at our example. It's still going to be kind of a pain, but it's going to be better. So instead of doing this, we're going to say that the variance is equal to the integral from 1 to 4 of x squared times our probability density function, which is 3/14 times x to the 1/2 dx minus the mean squared. I mean, it's still not nice, but it's at least, right, doing this integral is better than doing 3 different intervals. So it's definitely going to cut down on how much integration you have to do. So let's go ahead and do it. So it's going to be 3/14 times the integral from 1 to 4. X squared times x to the 1/2 is x to the 5/2. minus that number over there. So then integrating this, you're going to end up getting 3/14 times x to the 7/2 divided by 7/2 times 2/7, so times 2/7, x to the 7/2 from 1 to 4 minus 93/35 squared. And then plugging in, let's actually cancel. The 2 and a 2 cancel there. So you're left with 3/49. And then we have 4 to the 7/2 minus 1 to the 7/2 minus this 93/35 squared. 4 to the 7/2 is 2 to the 7th, and 2 to the 7th is, let's see. So if you're not good on your powers of 2, there's that 2048 game on your phone, which is a little addictive. Definitely helps you with your powers of 2. First part, so 2, 4, 8, 16, 32, 64, 128. So that's 2 to the 7th. So it's 128 minus 1, so that's going to be 127. So you have 3 times 127 over 49 minus 93/35 squared. And I would definitely not go any further in my simplification. I probably should have stopped sooner, in fact. But that's it. It's really, really nice. And then the standard deviation would just be the square root of that. So whatever that is, the standard deviation is just going to be the square root of this lovely number, what? 381 over 49 minus 93/35 squared. You should never, right? There's no formula to memorize for standard deviation. It is just the square root of the variance. So you should memorize the formula for variance if you're required to, and then you're like, wait, standard deviation is the square root. Okay, so that's an example of a continuous random variable where you can find all the things. Well, we found most of the things. There's one thing we didn't find, which we usually aren't asked to find, but we'll look at in another example. So let's look at some more examples. So all of these continuous random variables are probability density functions. It's all about integration. And the reason we're doing it, well, whoever was writing the book probably felt like you needed some sort of application. In the 21 series, the applications they see are more physics applications, but since a lot of people that take the 16 series don't have to take physics, they decided these were more relevant applications. So that's my very not great reason as to why we are doing this section. The real reason is because the math department decided that's what they're going to cover here, and that's what we're covering here. So yeah. All right, let's do this next one. Let's say that f of x is equal to, oh, this pen is, I think you're done. I think you get retired. The problem is I can't throw away my pens because you can throw them away, obviously, but I get the reusable cartridges and I should try to not throw them away. So I have stuff, so let me just put that there. I have a whole nother thing of ink. Are you red? Oh, you're red. Okay. I mean, red's fine too, but the black one's my favorite. Okay, so yeah. So f of x equal to k over x squared is a PDF, a probability density function, on the interval from 1 to 3. Find k. Okay, so all we're going to be doing is setting our integral over the whole entire interval equal to 1. Right? Because again, that's the requirement. Well, actually, first I should check out, is this function positive on that interval? Or I should say non-negative, really. Yes, this function is non-negative on the interval as long as k is positive. But we can figure out make k to be whatever we want it to be. So we will obviously make k be a positive number because it's going to have to be. So we're going to set the integral from 1 to 3 of k over x squared, or I would probably prefer to write k times x to the negative second, equal to 1. And in fact, if you wanted to, you could totally factor out, like I wouldn't normally do this, but if you want to, you could factor out the k and say that k is equal to 1 over the integral from 1 to 3 of x to the negative second dx. That would be a very, very, very lazy way of writing our answer, but it's technically correct, right? That's k. Okay, find it. Normally, we would do some of the integrating. I don't like integrating in my denominator if I don't have to. So I would write this as k times the integral from 1 to 3 of x to the negative second is going to be, well, let's just write that. So then we're going to integrate this. We're going to get k times the integral of x to the negative second is x to the negative first over negative 1 from 1 to 3 equal to 1. And then let's see here. I usually like to rewrite that. I would really rewrite that as negative 1 over x from 1 to 3. So plugging in the 3, we get negative 1/3, minus plugging in the 1, we get negative 1 over 1 equal to 1. Negative 1/3 plus 1 is 2/3. So we have k times 2/3 equal to 1. So then multiplying both sides by 3/2, we get k equal to 3/2. So f of x equal to 3 over 2x squared on the interval from 1 to 3 is a probability density function. And that's always kind of the gist that they mean when they're asking you to figure out what k is. You're always setting your integral equal, well, I should say, there's probably ways they could set up the problem to make it different, but virtually all the time, if they're saying, here is a probability density function with an unknown k, figure out what k is, you're taking the integral of that PDF and setting it equal to 1 and solving for k. Let's look at a couple other things with this PDF. So let's go ahead and find the expected value. So for this probability density function, f of x equal to k, so 3 over 2x squared. But you could also write it as 3/2 over x squared, but that feels weirder to me. I don't usually I try to avoid fractions and fractions if I can. So let's find the expected value. Okay, that's no big deal. Expected value, oh, I should say, right on the interval. Right, whenever you're talking about a PDF, you kind of have to specify the interval. If you don't, it's not necessarily a PDF. So let's see, the expected value is going to be the integral from 1 to 3 of x times your PDF. Okay, well then we're just going to simplify and integrate. I'm going to pull out 3/2. So I'm going to write this as 3/2 times the integral from 1 to 3. X times 1 over x squared is going to be just 1 over x. Integral of 1 over x is the natural log of the absolute value of x. So we get 3/2 times the natural log of the absolute value of x from 1 to 3. We plug in 3, we get 3/2 times natural log of 3. You don't need to write the absolute value of 3 because the absolute value of 3 is 3. Minus 3/2 times the natural log of 1. That's just 0. So our final answer is that the expected value is 3/2 times the natural log of 3. Okay. Instead, let's find the median. So the difference between the expected value and the how do you kind of describe? So again, right, the expected value is the weighted average, right? Basically, the further you are away from the mean, the more kind of importance you have. Whereas so in fact, actually, let's go ahead and look on Desmos. This is a great time to use our tools. So let me show you what I mean. Yeah, it's gonna be cool. Hopefully it'll be cool. It'll be interesting one way or the other. Hopefully Desmos will open. Come on, Desmos. So our function, right, f of x is equal to 3 over 2x squared. And we have an interval from what, x is between 1 and 3. So there's our PDF. Let's zoom in on it a bit. Okay. Might as well draw some vertical lines here to make it kind of look nicer. Cool. So here's the region we're looking at. In fact, if you really wanted, we could, sure. There's our region. And our mean, which we just found, was 3 halves natural log of 3. So if we look at x equal to 3 halves natural log of 3, that is the mean. And so the way I kind of think of the mean is it's where this would balance, right? If you thought of this pink region here as kind of being like a flat plate and you laid it down, that purple line in the middle would be the line it balanced on, kind of like a teeter-totter or a seesaw. Because although there's a different amount of area here than there is here, the area that's further away kind of has more leverage, right? It's very much a what's the word I'm looking for? What I'm really looking for is a moment of inertia kind of thing. But it's really just that things further away from your fulcrum exert more force, right? If you go further out on the teeter-totter, a small person can lift up a larger person. On the other hand, there's also something called the median. The median, which we'll find in a second here, is going to be worth exactly half the area on either side. So let's go back and find the median. But we'll come back to this. So again, the mean is the line where the area would balance. And the median is the line where half the area is on either side of it. Let me stop sharing. Let's go ahead and find the median. Where'd you go? Okay. So median, let's go ahead and look at our picture, right? Probably close this window, it's getting hot in here. Let me turn on my fan so it don't get too hot. Let's get this out. Fortunately, I'm in the warmest room in my house. It would be excellent if my wife and I could switch rooms because her room is usually the coldest and mine is the warmest, and we would like to be opposite, but all her stuff is set up over there already. So no dice. Okay, so and here's our PDF. And we're trying to find the place where the amount of area on the left is the same as the amount of area on the right. So it's probably somewhere, I'm sure it's less than 2. It's probably somewhere like right here. So there's the median, which you usually call lowercase m. And what should always be true is half the area should be here and half the area should be here. What we're going to do is we're going to say, okay, well, if this is half the area, then the integral from 1 to m of our function, which is 3 over 2x squared, that needs to equal 1/2. And that's always how you set up to find the median. You can do your integral from your lower limit to the median equal to 1/2, or it's also equally valid to do the integral from your median to your upper limit equal to 1/2. Both of these are valid ways of finding the median. Typically, you want to pick the one that seems like it has the easier limit of integration to deal with. I would probably choose this one because 1 always feels easier to plug in than just about anything else. So we're going to integrate this. we're going to get, let's see, this is 3 halves x to the negative second. The integral is 3 halves x to the negative first over negative 1 from 1 to m equals 1/2. Okay, let's simplify this a bit. I'm going to say that's a negative 3 over 2x from 1 to m equals 1/2. And then I'm going to plug in the m and the 1. So I'm going to have negative 3 over 2m minus negative 3 over 2 times 1 equals 1/2. So I'm going to say this is negative 3 over 2m plus 3 halves equals 1/2. So I'm going to subtract 3 halves from both sides. So negative 3 over 2m equals 1/2 minus 3 halves is negative 1. And then multiply both sides by negative, oh, actually multiply both sides by 2m. So then negative 3 equals negative 2m, and m is going to equal negative 3 divided by 2, which is 3 halves. Okay, so our median is 3 halves. And what we're saying, let's go back to Desmond here so we can actually see it look nice. What we're saying here, all right, so this line here, to the left of that line, all that area is exactly 1/2. And to the right of that line, all that area is exactly 1/2. And I really want to emphasize here, the median and the mean are almost always different. Occasionally, depending on your distribution, they can be the same. But for the most part, the median and the mean are different. The median is the place where half of the things are above it and half of the things are below it. You've probably heard the word median in news reports talking about like median household income, right? The median household income is the amount of money where half people in the usually nation make more than that and half people make less than that. Whereas the mean is usually much higher because there are people that make millions and millions or billions of dollars, right? And they definitely skew that data up. And so sometimes the mean is not a great, it's not a great statistic to tell us what the true center of something is or the meaningful center of something is. Often the median is a better measure of what the center of the data is, or a more meaningful measure of that. So statistics is very interpretive. Even though there's a lot of math in it, you have to still kind of use your common sense, for lack of a better word, to kind of figure out what things mean. I know you guys must have laughed at that. I know I can't hear you because everything's off, but I'm sure everybody just thought that was hilarious. So it's kind of one of the bummers about not teaching in person is I don't get to see all the smiling, laughing faces when I make terrible jokes, terrible statistics puns about things, meaning things. Anyway, let's do more examples. Let's see where we're at here. But yeah, so that's how you calculate the median, right? You're always taking your integral and setting it equal to 1/2, whether it's the integral from your lower limit to m or from m to your upper. So I'm not going to do it, but I think it'll be worth any of your time to actually show that this integral also gets you a value of m equal to 3 halves. I would recommend any and all of you to do that when we have a minute. Well, let's look at some more examples because I know people ask me a couple things. There's my notes. Yeah, people have some specific questions, which are very similar to what we're doing today, but let's go and look at their specific questions. Oh yeah, I can definitely see why this one was asked because this next one we're going to do is a little trickier. Do I want to change it up at all? I think you want to change it up. Let me actually, before I get crazy and start changing things up without looking ahead, let me see one thing. Sometimes I change a problem with a different number. I'm like, oh, that's fine. Sometimes I change a problem with a different number. It's like, oh, that was a terrible choice. No, I think this should be fine. Let me go ahead and look one more thing. Oh, interesting. Someone asked, oh, there we go. Okay, cool. I see. All right, cool. All right. So my question, yeah, my version of this question is slightly different from my version. So here's the setup. This is essentially problem 12 in Lee's homework. The time t in hours required for a new employee to successfully learn to operate a machine in the manufacturing process is described by the probability function f of t is equal to kt times the square root of 36 minus t, where t is between 0 and 36. Which makes sense, right? Because the t was smaller than 0, like t was -1. Well, first of all, negative time doesn't usually make sense. Second of all, negative time would give us a negative value here, assuming k is positive, which is going to be positive. And t can be bigger than 36, so the t was like 37, then you have a square root of a negative, which is definitely not in the domain of this function. So again, this is the time in hours to successfully learn how to operate a machine. Okay. So first things first, we're going to find k. So all of you should be able to answer the question. I'm not going to ask you to answer the question, but all of you should be able to answer the question, what would you do next to find k? Well, we're going to set something equal to something. And everybody, again, you all should be able to, in your head, be like, oh, I know we're going to set this equal to that. And the this equal to that we're setting equal to together are, we're going to set the integral of our probability density function over our limits of integration. We're going to set that equal to 1. And that's always or almost always how you're finding k. You're setting the integral of your PDF over the entire interval equal to 1. Great. So now we're going to actually figure this out. And to do this, we have to do a u sub with a back substitution. So we're going to let u equal 36 minus t. du is going to be negative dt. So negative du is going to be positive dt. And if I solve this for t, u plus t is equal to 36. So t is equal to 36 minus u. Okay, so check this out. Things get a little bit funky, but not that funky. So this is going to become the integral of, let's see, let's deal with the dt first. So dt becomes negative du. 36 minus t becomes u. And k times t becomes k times 36 minus u. And my limits of integration change. So if this is a t limit here, if t is equal to 0, u is going to be 36 minus t, which is 36 minus 0, which is 36. And if t is equal to 36, u is going to equal 36 minus 36, which is 0. Now, typically, we don't love our limits of integration being kind of in this wrong order. It's not really wrong. It just feels less than right. But we luckily have a negative sign here, so we can change the order and change the sign. So this is actually equal to positive integral from 0 to 36 of k times 36 minus u times u to the 1/2. And now we're good to go. We can distribute the 1/2, we can factor out the k. I'm going to erase this over here. This is equal to k times the integral from 0 to 36 of 36 times u to the 1/2 minus u to the 3/2. This is going to get a little bit gross. So then we get k times 36 times 2/3 times u to the 3/2 minus 2/5 times u to the 5/2 from 0 to 36. We don't need to plug back in t, although we could. You really don't, right? Because these are our u limits. So we're just going to plug in those values for u. So we're going to get k times 36 times 2/3 is 24. 36 to the 3/2 minus 2/5 times 36 to the 5/2. And that's supposed to equal 1. Okay, I definitely need a calculator here because 36 to the 5/2 is a little bit big. Let's see what we've got. We've got, so k times, oh, I'm sorry, and if we plug in 0, you get 0, right? 0 to the 3/2 is 0, 0 to the 5/2 is 0. So let's see, k times 24 times 36 to the 3/2 is 6 cubed, which is 216, minus 2/5 times 36 to the 5/2, which is 6 to the 5th, which I don't know. It's 6 to the 5th is 7,776. It's not divisible by 5. And that's supposed to equal 1. All right, so let's simplify this a little bit. 24 times 216. That's 5,184 minus 2/5 of 7,776. You get 2,073.6. So k times, which is a fraction, would be I never know how to make this thing make fractions. Anyway, you get, I said a number, I forget what it was. Sorry, 24 times 216. All right, divided. Minus that number there. Anyway. Yeah. So you get k equal to 1 divided by 2073.6. That's gross. Yeah. Yeah. Sorry, one second. So yeah, which is 5 divided by 10,368. That's kind of a terrible number for k. I'm not gonna lie. Like that just seems so definitely this. So the person who asked me this problem, theirs was instead of kt times 36 minus t, there's this kt times the square root of 4 minus t, which is probably going to try to be a little bit nicer. So then we can ask questions. The questions like, determine the probability that the new employee will learn to operate the machine in less than 6 hours. So that's actually not terrible. Ooh, interesting. So, so there's something I've done here that's going to make the next question a little bit harder than it should be. So doing the u sub and not changing back to t means we don't exactly have the integral exactly the way we want it, right? I can't just take this integral and plug in 0 to 6 and have it come out exactly right. I don't think. No, I definitely can't. That's a bummer. So instead, what I would probably, yeah. So let's go ahead and take our answer here. And let's go ahead and I really don't want to. Fine, we'll do it anyway. So what's the probability that the time is between 0 and 6? So we're going to take our integral of k times f of x dx. Instead of doing the integral from 0 to 36, like we just did, we're going to do the integral from 0 to 6. Now, it's going to be kind of gross still, right? It's going to be, this problem is really like, this last problem is a little bit gnarly, I'm not going to lie. All right, so our k value is this lovely number here. I already forgot what it was. Times the integral from 0 to 6 of our function. T, oh, sorry, I used x, I should use t. T times the square root of 36 minus t. Now, the integration process is still the same as it was before. You're still doing the use of, where u is 36 minus t, du is still negative t dt, sorry, negative dt. So that negative du is positive dt. This becomes 5 over 10,368. Integral from let's change it into integration. So that's going to be, if t is 0, u is going to be 36. If t is 6, u is going to be 36 minus 6, which is 30. And then we have t, which is equal to 36 minus u times the square root of u. Minus. All right. So then, now we know the integral of this, right? The integral of 36 squared u minus, right? We know the integral of this is just going to be 36 times 2/3 u to the 3/2 minus 2/5 u to the 5/2. So that's at least something we don't have to kind of create. We're going to be, I'm going to change this and these to be the positive 5 over terrible number integral from 30 to 36 of 36 squared to u minus u to the 3/2. And then that's going to be 5 over 10,368 times, we know this is going to be 24 times u to the 3/2 minus 2/5 times u to the 5/2 from 30 to 36. So I guess we probably could have not done all that again if we kind of looked at what our u substitution was and said, okay, the last time we made u equal to 36 minus t, and we ended up with the integral from 0 to 36. But now, and we started with 0 to 36, but now since we're going from 0 to 6, our 0 became 36, and our 6 became 36 minus 6, which is 30. I'm just trying to hopefully show you that if you've already done the integral once to find k, you shouldn't really have to do the integral again to find just some probability. It's to figure out what your means of integration are. It's a little bit more challenging when you have a different when you have a u substitution that you're doing in your integral. So if we do this, it's really not going to be nice. Right, this is kind of terrible. It's going to be the number we calculated before. Oh, that's interesting. So it's going to be, so here's what I know. I know that when I plug in 36 here for these two things, I know this number is equal to the reciprocal of that number. So I'm going to get 5 over 10,368 times, when I plug in 6, I do in fact get 10,368 over 5. So I'm going to plug in 36, I get that. And when I plug in 30, it's super incredibly awful. It's 24 times 30 to the 3 halves minus 2/5 times 30 to the 5 halves. And there's really nothing you can do about that. It's just gross. I would probably just type that giant mess into WebWork and be done with it. And then for the second question, same idea. The second question I have is determine the probability of the new employee will learn to operate the machine in more than 7 hours. So for that one, instead of going from 0 to 6, you would go from 7 to 36. Right? That's the probability of operating in more than 7 hours. And so then this would be 7, this would be 36. This would turn into 36 minus 7, which is 29, and this would turn into 36 minus 36, which is 0. So then this would be 0 to 29. All right, so again, once you've done the integral once, you just have to figure out what your new limits of integration are for other questions about what the probability of something happening is. Okay. Oh yeah, there was another one. Let's see which one of those is more interesting. Yeah, let's do this one. And numbers sometimes, so I feel like sometimes Weber problems are like, someone's like, sure, I'm sure they'll be okay, and they didn't actually ever check how terrible the numbers really were. Sometimes the numbers are like really awful, and sometimes they're just fine. But let's look at this one. I want to know, so I want to show that f of x equal to equal to, I'm more of a find. Let's find k such that f of x equal to k times x times 1 minus x squared is a PDF. And then we'll probably find the mean and the median. So we're going to set the integral. Oh, I didn't give you a limit to integration. Sorry. PDF on the interval from 0 to 1. So the integral from 0 to 1 of k times x times 1 minus x squared dx has to equal 1. And just like the previous problem, this is another situation where we have to do a u sub with a back sub. So we're going to, that's not entirely true. You could totally do this problem without doing any substitution. You can just multiply that. So one option would be to do this as the integral from 0 to 1 of k times 1 minus x squared is 1 minus 2x plus x squared. So then multiply that by x, and you get x minus 2x squared plus x cubed. That is one option that's totally legit. You do it that way, you get k times x squared over 2 minus 2x cubed over 3 plus x to the 4th over 4. From 0 to 1. And plug that in, you get k times 1/2 minus 2/3 plus 1/4 minus 0. Common denominator is 12. So you get k times 6/12 minus 8/12 plus 3/12, which is 9/12 minus 8/12 is 1/12. So you get k over 12 equal to 1. So k equals 12. Or you could have done the u sub, which I think is worth seeing. So you could have said u is 1 minus x, du is negative dx, and negative du is positive dx. Then this integral becomes the integral of, let's see, k times x is equal to 1 minus u, not squared. And 1 minus x is u, commonly squared. And my new limits of integration, well, if x is 0, u is 1 minus 0, which is 1. And if x is 1, u is 1 minus 1, which is 0. And I forgot the negative sign, because it's a negative u. And then I do the usual thing where I have a negative, and these are out of order, so I just get rid of the negative and switch the order. So this is equal to the positive integral from 0 to 1 of distribute the u squared minus u cubed. Integrate, you get u cubed over 3 minus u to the fourth over 4, 0 to 1. So you get k times 1/3 minus 1/4 minus 0. 1/3 minus 1/4 is 4/12 minus 3/12, which is 1/12. So again, we get k over 12 equal to 1, which gives us k equal to 12. I probably would prefer to do it this way here, but if this was instead of 1 minus x squared, like 1 minus x to the 10th, then you don't want to multiply it out. You definitely want to do this u sum with the back. So yeah. Let's go ahead and ask ourselves, what's the median? The median's a question I feel like, actually, let me try, like, is there any median questions in your homework? Yes. Doesn't look like it. I don't want to get too carried away with my medians here before and you guys don't have to. Yeah, it's not like, yeah, I don't see any median questions. Let's not ask the median. Let's ask, we got time, we got 4 minutes. Let's find the mean in the standard deviation. So, yeah, it's going to be kind of this. So our PDF, right, is f of x equal to 12x times 1 minus x squared. Next, let's find the mean. So that's going to be the integral from 0 to 1 of x times all that. And that square should be on the outside of the parentheses there. Here, I probably would just multiply it out. So I'm going to take my previous integral and just multiply everything by an x. So it's going to be x squared minus 2x cubed plus x to the 4th times 12. From 0 to 1. And then we're going to get 12 times, let's see, x cubed over 3 minus 2x to the 4th over 4, cancel 2, plus x to the 5th over 5, from 0 to 1. So that's going to be, let's see, 12 times 1/3 minus 1/2 plus 1/5. It's a great thing about the limits of integration being 0 to 1. If everything's a power of x, you just plug in 1 and get your coefficients. So that's going to be 12 times, let's see, it looks like 30 is my common denominator. So I've got 10/30ths minus 15/30ths plus 6/30ths. 10 plus 6 is 16, minus 15 is 1/30. So you've got 12 over 30, which reduces to 2/5. Okay, now to find the variance, we're going to use the alternate formula. So for the variance, we're going to say that the variance is the integral of x squared times f of x from 0 to 1 minus our mean squared. In this case, is going to be the integral from 0 to 1. I don't know why I bought, I feel like I have enough room to do this here. X squared times 12x times 1 minus x squared dx minus 4 over 25. Well, that's not too terrible to calculate. So this integral here is just going to be this integral times another factor of x. So that's going to be the integral from 0 to 1 of x cubed minus 2x to the 4th plus x to the 5th. Right? I know that for the mean, I just took my integral and multiplied everything by x to get x squared minus 2x cubed plus x to the 5th. And for my variance, I took and multiplied by another x. Like this. So, and then minus 4 over 25. Then we integrate, we get x to the 4th over 4 minus 2x to the 5th over 5 plus x to the 6th over 6, 0 to 1 minus 4 25ths. We plug in and we get some numbers. Let's see, we get 1/4 minus 2/5 plus 1/6 minus 4 25ths. That looks terrible, but we get something. I don't know. Common denominator could be something terrible, like a lot. Let's look at these three things. Yeah, even that's not a big common denominator. I think it's like 60. Yeah. So this is 15 over 60 minus multiplied by 12 over 12, 24 over 60 plus 10 over 60 minus 4 over 25. And interestingly enough, this ends up being 1 over 60. It's kind of interesting that each of these kind of end up being 1 over their thing. So that's 1 over 60 minus 4 over 25. Which seems like I've made a mistake. And here's why. The variance is supposed to be positive all the time, right? No ifs, ands, or buts about it. So I feel like I've made an error here. I'm not seeing what it is.